Welcome everyone. Today we're diving into Module 1, Introduction to Euclidean and Non-Euclidean Geometry. We will explore the fascinating ways geometry helps us understand and shape the world around us. This chapter takes us from classical ideas of shapes and space to more abstract and modern interpretations. We will understand both Euclidean and non-Euclidean geometry and see how they appear in real-world and creative contexts. First is the Euclidean geometry. Think of this as a normal geometry or the kind of geometry most of us have learned in school. It's a kind of geometry that deals with flat surfaces like a piece of paper on the floor. It was developed a long time ago by a Greek guy named Euclid. So it was in 300 BC. In this geometry, things make intuitive sense. For example, the shortest path between 2 points is a straight line, and if you draw a triangle, the angles always add up to 180 degrees. Okay, now let's have this Euclid's 5 postulates. So these are just 5 basic rules that all of Euclidean geometry follows. So here are just a few. The first postulate is that a line can be drawn between any 2 points. Here we could always draw a straight line between 2 points, just like the figure that I have shown you in the previous slide. The second postulate is that a line can be extended indefinitely. So it is true that lines can go forever. We could always extend the line to the right or to the left direction or upward or downward directions too. The third postulate is that a circle can be drawn with center and radius. So we have known this, that given a center and the radius of a circle, we could always draw a circle. And then we all know that all right angles are equal because all right angles measure 90 degrees, so they are all equal. The fifth postulate, the parallel postulate, is the most interesting one. So if 2 lines are heading in the same direction and never cross, they are parallel, or they will intersect only if the angles between them is less than 180 degrees. But if their angles measure 180 degrees, then for Euclid, these are parallel lines. It's this last one, or the parallel postulate, that other types of geometry started to question. Now, this is where things get weird and exciting. People ask, what if the space isn't flat? That's when we get non-Euclidean geometry, which breaks that last rule about parallel lines. There are 2 main kinds of non-Euclidean geometry. The first is that we have the hyperbolic geometry, and the second one is the elliptic geometry. This helps us understand things that flat geometry can't, or like how the universe works or how GPS finds your location. Okay, now let's have hyperbolic geometry. Imagine you're walking on a curved surface. If you pick a point and draw lines that don't touch another line, you can draw an infinite number of them. That's way different from the one-line rule in Euclidean geometry. Also, if you draw a triangle here, the angles add up to less than 180 degrees. So here is an example of a hyperbolic geometry, and particularly the Poincare geometry. This fascinating image is a representation of hyperbolic geometry that is a popular way to visualize the strange curved surface of hyperbolic geometry on a flat surface. Imagine a world where as you walk toward the edge, the space keeps stretching. You never reach the boundary, but everything seems to get smaller and more distant. That's the magic of hyperbolic geometry. In contrast, elliptic geometry describes a curved surface where no parallel lines exist. Imagine you're drawing shapes on a ball. In this world, parallel lines don't exist. All lines eventually meet, just like the lines of longitude on a globe. That's why airplane routes look curved on a map, but they're actually straight lines on the globe. To sum up the real-world application, Euclidean geometry appears in daily tasks like building and measuring. Hyperbolic and elliptic geometries appear in more advanced areas like navigation, astronomy, and even theoretical physics. This ends the introduction for modern geometry. I hope you were able to grasp the differences between Euclidean and non-Euclidean geometry. Thank you very much.